Hello, these are the solutions to AP Physics C suggested problem set number 7.1, the minimum suggested problems, as you can see up here. We also have some additional suggested problems, and these are all related to rotational motion. So to kick it off, we have a conceptual question, or two questions rather, where we have a bike chain, and we have two sprockets that are connected by a chain, and all points on this chain have the same linear speed. So all points on the chain have the same linear speed. So that is given here as v. And the question asks us, is the magnitude of the linear acceleration also the same for all points on the chain? So if you recall back to just linked mass problems in forces, we know that since all of these pieces of chain are linked together, they all have the same v. They all have the same velocity. Actually, I should say speed in this case, since it's not actually a velocity. So in order for them to have all of the same speed, that means when one moves, the next one has to move exactly the same way. So that means that if this chain accelerates, all pieces of the chain must accelerate. So all pieces must have the same acceleration because they all must move together. So therefore, the linear acceleration must be the same throughout the chain. So we'll say that for all chain links. Now, the second part of this says, how are the angular accelerations of the two sprockets related? So now we have a couple different situations. So firstly, we'll look at angular speed. So we know that acceleration is the same for every point on the chain. So that's the linear acceleration. Now what does that mean for us? Well, since everything around this has to be moving, that means that a tangential for each sprocket has to be the same. And again, the reason for that is because the linear acceleration has to be the same. So, since the tangential acceleration is this acceleration here, right, and that's at all points tangent to my sprocket, then how does that relate to angular acceleration? So angular acceleration, if you recall, is actually going to be the tangential acceleration of a particular turning device or rotating object divided by the radius of that object. So while the radii are not the same, the tangential acceleration is the same. So because the sprockets have different radii, that means that our angular accelerations must be different. So because they have different radii, alpha is going to be different. So how are those two related? The way we relate them is kind of through this radius. So alpha of, let's say, the front sprocket is going to be tangential acceleration, which is the same for everybody, over the radius of the front sprocket. Similarly, alpha of the rear sprocket will be, again, the same tangential acceleration, just divided by the radius of the rear sprocket. I'm going to do a big R here. So, how are these two related? Well, they're just related, it seems, through this ratio of radii. So I can solve one of these for the tangential acceleration. So let's just solve this front angular acceleration for it. So I have angular acceleration of the front sprocket times the radius of the front sprocket. and then I just plug that into what I have here. So I have alpha, the angular acceleration of the rear sprocket, is equal to alpha of the front sprocket times really what ends up being the ratio of the radii. So I can rewrite this and say that alpha of the rear sprocket is equal to the ratio of the rear and front radii times the alpha of the front radii. So, what does this mean? Well, if the front radius is larger, that means that the angular acceleration of the rear sprocket is going to be bigger. And this seems to make sense, right? For some small amount of acceleration on this bigger sprocket, we will have a quicker acceleration in the back, which is good. This confers mechanical advantage in our bicycle. Now, to follow this up, we have question 9.5, or Q 9.5, that asks, how are the radial accelerations, so not tangential acceleration, how are the radial accelerations of points at the teeth of the two sprockets related? So this is another situation where, so I'm going to write 9.5, this is another situation where we need to consider how things are the same for each sprocket and how they are different. So the radial acceleration can be found a couple different ways. We can say it is v tangential squared over r, or we could also say it is omega squared times r. So for the front sprocket, the radial acceleration, so I guess I'll have to say r radial front, is going to be v tangential squared over the radius of the front sprocket. And so why am I going to do it in terms of v tangential? Well, v tangential is the same for both sprockets. That is stated explicitly. So that is the easiest understanding. Now, is angular speed the same for both? Not really. Because if you think about it, this larger sprocket is going to turn fewer times for every turn of the small sprocket. So my radial acceleration is best compared through the tangential velocity. So my radial of the front sprocket is written here, and the radial acceleration of the rear sprocket is, again, v tangential squared over the rear radius. And so now how do I relate these? Well, I do the same trick I did for the angular acceleration, which is I solve for the similar or the same identical component. So for the radial velocity, that's going to be my tangential velocity squared, and that's just going to be a radial for the front times the radius of the front is equal to my tangential velocity. And so for this comparison, I have radial acceleration for the rear is going to be equal to radial acceleration. Actually, I'm going to go ahead and skip to this. So I'm going to do the ratio of the radii times the radial acceleration of the front sprocket. So the point in doing this is to show you how these are related. So when I have two interlinked sprockets, you see that this ratio of radii just shows up every single time. So something to look out for all problems that involve a linked set of rotating objects. For question 9.6, we're given an angular position rather, as a function of time. So even though this says calculus already as the problem type, you should know to use calculus based off the fact we're given a time-dependent function. So theta as a function of time is going to be 250t minus 20t squared minus 1.5t cubed. So I'm going to go ahead and rewrite that. And now I can go through this and say, at what time is the angular velocity of the motor shaft 0? So I know that angular velocity as a function of time for my shaft is going to be the derivative of theta with respect to time. So I'm going to go ahead and take the first derivative of this function. So that will be 250 minus 40t minus 4.5t squared. So this right here is my omega. So all I need to do when I want to find when the angular velocity is equal to 0 is set this quadratic equation equal to 0. So 0 will equal 250 minus 40t minus 4.5t squared. So from here I just need to solve the quadratic equation. So I'm going to go ahead and write. I'm going to use a calculator to do this. You may do whatever method you choose, but I'll pause for a moment and let you do that. And so from my calculations, I get two values. I get t of about -13 and a t of about 4.234. Now, which of these do I want to use? Well, this negative time occurred in the past, so I probably don't want to use this. So I'm going to reject this one because it was in the past, before the event actually happened. So I'm going to use this time as my answer. Now, question B says, calculate the angular acceleration at the instant the motor shaft has 0 angular velocity. So, for part B, I know that alpha is equal to, in this case, d omega dt. I could do also the second derivative of theta, but I already have a function for theta, so I'll just do a single derivative and call it a day. So from my omega function, the derivative is going to be -40 minus 9t. And I want to find the value of this when the angular velocity is 0. So that is at this time. So I want to find alpha of 4.234. So I'll simply plug in those values. So that'll be 4.234. And I'll find that the angular acceleration at that instant in time will be equal to approximately -78.1, and we'll say this is in radians per second squared. So, for part C, we are asked how many revolutions does the motor shaft turn through between the time when the current is reversed and the instant when the angular velocity is 0. So for part C, it's asking us, For part C, it's asking us the delta theta. So what angle has it turned through in revolutions between time 0, so from t equals 0 to t equals 4.234 seconds. So my delta theta will just come from my theta function. So zooming in here, we have delta theta is equal to theta of 4.234 seconds minus theta of 0. So for this particular function, we go back up here, we have 250 times 4.234 minus 20 times 4.234 squared minus 1.5 times 4.234 cubed. And then since all of these terms include a t, that means that theta of 0 will just be 0. So my delta theta in radians is going to be about 586 radians. Now we're asked through how many revolutions has it turned. So I need to convert radians to revolutions. So how do I do that? Well, recall that 2 pi radians is equivalent to 1 revolution. So I will multiply by 1 revolution per 2 pi radians. So even though radians aren't a unit, that really is the ratio that they are related in. And so dividing this number by 2 pi, I would get about 93, and I guess we'll just round it to 93.3 revolutions. So that's part C. Now backing up to look at part D, it asks us how fast was the motor shaft rotating at t equals 0. So in order to find this, I want to find instantaneous angular speed or angular velocity. And so I want omega of 0. And so I'm going to take my omega function that I found right here, that is 250 minus 40, plug in my 0 for the time, minus 4.5 times, again, the 0, squared, and I see that my initial angular velocity or angular speed is 250, and that would be in units of radians per second. Now, finally, we have part E that says calculate the average angular velocity for the time from t equals 0 to the time calculated in part A. So for E, I'm going to zoom in here, omega average is going to be equal to omega 2 minus omega 1 over, actually, we're trying to try this differently. So we're going to make this delta theta over delta t. So I just found delta theta as 586 radians. So that means I can just say 586 radians for my change in angle for this time period over the 4.234 seconds minus 0. So my average angular speed for this time interval is approximately 138 radians per second. So this is really just different applications of our kinematics and differential calculus. For question 9.11, the rotating blade of a blender turns with a constant angular acceleration of 1.5 radians per second squared. So alpha is equal to 1.5 radians per second squared. How much time does it take to reach an angular velocity of 36 radians per second starting from rest? So for part A, we're looking for time. We have a final angular velocity of 36 radians per second, and we're starting from rest. So omega naught is equal to 0. So what equation includes all of these? Well, that would just be our first kinematic equation, omega equals omega naught plus alpha t. So here I'm going to solve for time, and that becomes omega minus omega naught over alpha. So substituting variables here, we have final angular speed is 36 minus 0 over my constant angular acceleration of 1.5 radians per second. So the time here is simply 24 seconds. Nothing to it. Now for part B, it says, through how many revolutions does the blade turn in this time interval? Now we actually have a couple choices. So we can say either delta theta equals omega naught t plus 1/2 alpha t squared and solve for delta theta. Or we can use, if we really want to, omega squared equals omega naught squared plus 2 alpha delta theta. Either method is perfectly acceptable. Now, if you're at all unsure about your answer to part A, option 2 is the better choice because it does not depend on the time that you found in part A. So that's the option I'm going to choose. So I am looking for delta theta in this case, and delta theta, if I rearrange this, would be omega squared minus omega naught squared over 2 times alpha. So substituting values here, I know that omega naught squared is 0. So my equation simply becomes 36 radians per second squared over 2 times 1.5. So the angle through which we turn here is 432 radians. Now, the question actually asks, how many revolutions does the blade turn through? So since this angle is in radians, I need to convert radians to revolutions. Well, 1 revolution is equivalent to 2 pi radians, right? 1 complete circuit of a circle is 2 pi radians. So my actual angle rotated through in revolutions is approximately 68.8 revolutions. So for this problem, we are just simply doing some very basic rotational kinematics. For question 9.16, we are given that at time 0, a wheel has an angular speed or velocity of 24 radians per second. So I know that this is my initial angular velocity. So I'm going to write that as omega naught equals 24 radians per second. It has a constant angular acceleration of positive 30 radians per second. So alpha is constant and equal to 30 radians per second squared until a circuit breaker trips at t equals 2 seconds. So this is for 0 to t. Actually, yeah, we'll go ahead and write it this way, to 2. From then on, it turns through 432 radians as it coasts to a stop. So I know that delta theta in this case is 432 radians, and that should be positive because it's moving in the positive rotation direction, until it coasts to a stop, which means that omega will eventually be equal to 0. So A asks, through what total angle did the wheel turn between time 0 and when it stopped? So I know that during the stopping portion, so this is while it is slowing, the wheel has turned 432 radians. So now, for part A, I'm going to say, all right, I need to figure out how far it has turned for this portion of time. So delta theta will be equal to omega naught times t plus 1/2 alpha times t squared. So my delta theta for this 2-second interval is going to be 24 radians per second times the 2 seconds for which it is accelerating, plus 1/2 times my angular acceleration of 30 radians per second squared, times my 2 seconds again squared. So the angle that I rotate through for just this 2 seconds is 108 radians. So that is the portion for the first 2 seconds. So now I need to add that to what happens while it's slowing. So that means that my total angle rotated through is going to be 108 plus the 432 radians that are rotated through while it's slowing. So my total angle rotated through is going to be 540 radians. Now, for part B, it says, at what time did it stop? So for part B, we need to know a couple things. So we can figure out how fast it is moving, and then so we have a few equations we can work with here. We have omega equals omega naught plus alpha t. Now, unfortunately, we don't know alpha while it's slowing. So we know everything except for alpha while it's slowing, and we don't know time either. So this equation is not enough by itself. We also have delta theta equals omega naught t plus 1/2 alpha t squared. So this is the same problem. We don't know alpha while it's slowing, and we don't know time still. So this equation is not enough by itself. And finally, we have our other equation, which is omega squared equals omega naught squared plus 2 alpha delta theta, which is our third kinematic equation. And here we have every single bit except for alpha. So we can use this equation to find alpha. So let's go ahead and do that, since we need alpha, it appears, to find any of our to find our time. So in this case, I'm going to use this equation, and I'm going to solve it for alpha. So alpha would be equal to omega squared minus omega naught squared over 2 delta theta. So substituting some values here, I know that final angular speed is 0. And so I'm going to have negative initial omega. Now, actually, I don't have initial omega, do I? I only know final omega. Well, that doesn't really help me. So I need to figure out what that initial omega was. So I actually have to go back over here and find omega initial. So omega initial is really equal to omega final after 2 seconds, which is going to be omega naught. So we're going to say this is omega naught 2 plus alpha t for this, the first 2 seconds, for 2 seconds. So this omega naught 2 that I'm looking for is going to be equal to my 24 radians per second plus the 30 radians per second squared acceleration times 2 seconds. So my actual initial angular speed before it starts to slow down is going to be 84 radians per second. So now I can take this back in here. So I have negative 84 squared over 2 times the 432 radians that it rotates through during this time. So just in case you got lost in this, we're doing this in 2 parts. This is the first 2 seconds again to get the initial speed at the 2-second mark. And then from there, it slows down at some constant rate, we're assuming. So my angular acceleration ends up being negative 8. We'll just say 167 radians per second. And now I can go into one of my previous equations and find that time. So I'm going to go ahead and use this first equation. And so from equation 1, I would know that time is equal to omega minus omega naught over alpha. So since my omega is 0, that means that the time here will just be negative 84 divided by negative 8.167. So my time spent slowing down is going to be approximately 10.3 seconds. Now, am I done? Let's see. It says, at what time did it stop? Well, this is actually the 10.3 seconds after the 2-second mark. So what does that mean? That means that the actual stop time is going to be at t equals 10.3 plus 2, so 12.3 seconds. Now, part C asks us, what was its acceleration as it slowed down? Thankfully, we already figured that out. So for part C, which I guess I'll do in pink, we have this acceleration while it's slowing down. So there is an alternative way to get through this. As we did with kinematics, there's more than one way to solve these problems. So if you went through part B a different way, that is perfectly acceptable. There's more than one way to solve these kinematics problems. For question 9.21, we have a wheel of diameter 40 centimeters. So I'll just sketch a quick wheel. And it has a diameter, we'll call it D, of 40 centimeters. It starts from rest, which means that our omega naught, our initial angular speed, is 0. And it has a constant acceleration, or angular acceleration rather, of 3 radians per second squared. Compute the radial acceleration of a point on the rim. So I'm going to pick a point on the rim, and I want to find the radial acceleration. So I'm actually going to change colors here. So we have the radial acceleration. So this is a radial. At the instant the wheel completes its second revolution, so at delta theta equals, so how many radians? So it would be 2 times 2 pi radians, or after 4 pi radians. So I'm going to do that 2 different ways. I'm going to use omega squared r and v squared r. So for the first part, I know that the radial acceleration is going to be equal to omega squared r. So first I'm going to find r. So r is just equal to the diameter divided by 2, or 40 centimeters divided by 2. So that's just 20 centimeters. Now, as we discussed in class, I don't necessarily need to convert this to meters, as the only real stipulation for units is that everything is in the same units. Now, the next part, the stipulation for linear units is that they're in the same units. Our angles do need to be in radians. So the second part is I need omega in order to figure this out. So I'm given omega naught, I'm given alpha, and I'm given delta theta. So I have omega naught, alpha, and delta theta. So out of these, I know, and I want to find omega. Sorry, that actually looks like a W. Unacceptable. So omega is my unknown. So I'm going to use the third rotational kinematic equation, which says omega squared equals omega naught squared plus 2 alpha delta theta. So here I'm looking for omega. Now, my initial angular speed is 0, so I can go through and say omega is equal to the square root of 2 times alpha times delta theta. So substituting some values here, I have alpha is 3, and I have my delta theta as 4 pi radians. And so my final angular speed will just be about 8.68 radians per second. Now, what I need to do is plug it back into my radial acceleration equation. So my radial acceleration will be equal to this omega squared, so that's 8.68 squared, times my radius of 20 centimeters. So I'm going to write the centimeters because since I didn't convert it to meters, I need to make sure that my radial acceleration has appropriate units. So plugging this into my calculator, I find my radial acceleration will be 1,507 centimeters per second squared. Now, if you wanted to convert it to meters, that's pretty easy. Like, you still just divide by 100. So I could say this is also 15.07 meters per second squared. Either one would be acceptable. Now for B, it asks me to use the other relationship to radial acceleration, which is v squared over r. Now the thing that's important here is that this is a linear velocity, and in fact it is tangential. So I need to find that tangential velocity. So how do I go about doing that? Well, there's a couple different ways. I could take my omega here and relate it to tangential velocity. I know that tangential, actually let me move it up a little bit. So I know that v tangential is equal to the radius times omega. So my angular speed or angular velocity. So v tangential is just, in this case, my 20 centimeters times my angular speed that I already found of 8.68 radians per second. So v tangential in this case is going to be 173.6 centimeters per second. So now I can bring down my radial acceleration equation and substitute 173.6, square it, divide by 20. Now keep in mind this is centimeters per second, and I'm squaring that, and this is centimeters. So they're all in the same linear units, so this is acceptable. And I find out that my radial acceleration is, surprise, surprise, the exact same. So either one of these methods is perfectly acceptable for calculating radial acceleration. In fact, you will find that it is more convenient in some cases to do one over the other. So you need to be well versed in both. For question 9.23, we have a flywheel with a radius of 0.3 meters. So I'm going to go ahead and sketch me a wheel. It has a radius of 0.3 meters. And it starts from rest, which means its initial angular velocity is 0. It has an angular acceleration of a constant 0.6 radians per second squared. And I want to compute the magnitudes of the tangential acceleration, the radial acceleration, and the resultant acceleration. So I'm going to go ahead and write this out because this is a lot. We have a tangential, we have a radial, and then we just have a. Maybe we'll call that a net. So I need to find all three things. Now, when do we find them? For part A, we're finding this at the start. So for A, we want to find things when it is the case that omega is equal to omega naught, which is 0. And we know that time is equal to 0. So how do we find all of these? Well, we can choose any way that we want to. So let's go ahead and do the one that we know that relates to omega. So a tangential that we just found is equal to omega squared r. And since omega is 0, that means my tangential acceleration is 0. Is that correct? The answer is no. So you have to be very careful here. So this is a common mistake. This is not what we want to do. because it's easy to get these formulas confused. This is not tangential acceleration, and I bet you didn't catch that. This is, in fact, radial acceleration. So how am I going to know the difference? Well, my tangential acceleration is the one that is related directly to the angular acceleration. So that is going to be the one that is r times alpha. My radial acceleration is the one that has the squared term in it. Please commit that to memory. So this is not equal to 0. The radial acceleration is equal to 0 at this instant. The tangential acceleration, however, is going to be equal to 0.3 meters times 0.6 radians per second squared. So my tangential acceleration in this case is going to be 0.18, and that's going to be in meters per second squared. So I have a 0 radial acceleration, and I have a tangential acceleration of 0.18 meters per second squared. And so my net acceleration is just going to be, in this case, I'm going to go ahead and write this over here. A net is going to be A tangential squared plus A radial squared, all square rooted. So, since radial is 0, that means that my net acceleration is just equal to the tangential acceleration. So for this instant, A net is going to be equal to the 0.18 meters per second squared. Now that is just for that instant, because when we go to B, we want to know what's happened after it has turned through 60 degrees. So delta theta is equal to 60 degrees, which in radians would be, well, we have to multiply by pi over 180. We would end up with approximately 1.047 radians. And so what is the angular speed at that instant? So we need omega, which is equal to omega naught plus alpha t. We can't use this equation. We need one with theta in it. So let's use delta theta equals omega naught times t plus 1/2 alpha t squared. So is this the one we want to use? We don't really know anything about time. We only know about angle. So again, we don't want to use this one. So our only remaining choice really is our third kinematic, which is independent of time. Perfect. We don't know anything about time. So that's why we want to use this equation. Now, omega naught is 0, which means omega will just be equal to the square root of 2 alpha delta theta. So this will be the square root of 2 times our angular acceleration, which is given to be 0.6, times our angle in radians, 1.047, square rooted. So omega, for this case, ends up being 1.12 radians per second. Now we can go in and calculate our radial acceleration. So our radial acceleration is going to be omega squared r, which in this case is going to be 1.12 squared times our radius of 0.3 meters. So our radial component of acceleration ends up being approximately 0.377, and that's meters per second squared. Now our tangential acceleration has not actually changed, and the reason I know that is because the radius has not changed and the angular acceleration has not changed. So my tangential acceleration is the same as it was initially. So this is 0.18 meters per second squared. Now, however, we need to find a new net acceleration. So I will have the square root of my tangential component and radial component squared. So I have 0.18 squared plus 0.377 squared, and then square root all of that, and my net acceleration magnitude is approximately 0.418 meters per second squared. Now to move on to part C, we again need to find the omega, the angular speed at that particular moment. So now it's turned through 120 degrees. So my delta theta, which is equal to 120 degrees, we need to convert to radians again. And so this is going to be pretty much twice that before. So it's 2.094 radians. And I already know that I need to use this third kinematic equation. So omega squared will be equal to, again, same initial omega, same initial angular velocity. So my omega, my angular velocity, can actually be written again straight up as square root of 2 alpha delta theta. So this is the case when initial angular velocity is 0. And so substituting here, I would just have the square root of 2 times 0.6 times my 2.094 radians. So the angular speed at this instant in time is 1.585 radians per second. And so now when I go to calculate my radial acceleration, I'm again using omega squared r, which in this case would be 1.585 squared times my radius of 0.3 meters. So my radial acceleration is 0.329, pardon me. Sorry, I take that back. I read my calculator wrong. 0.754 meters per second squared. So that's my radial component of acceleration. And now my tangential component, since that is equal to just r times alpha, is still the same as it was this entire time. And so that's going to be still 0.18 meters per second squared. And that means that my net acceleration will be the square root of 0.18 squared plus 0.754 squared. And that gives me a net acceleration magnitude of 0.775 meters per second squared. So the purpose of this question is to really drive home the difference between radial acceleration, tangential acceleration, and that net acceleration for an object. So in case you've missed the actual conceptual side of it, we see that the tangential acceleration is constant for a constant angular acceleration. And then we see that the radial acceleration changes over time with the changing angular speed or velocity.